Hello friends, this is AP Calculus section 3.1 notes. Today is the day you've been waiting for. Today is the day we are going to start learning all of our differentiation rules. And we are going to start with the absolute best one, which is the power rule. You're going to both love me and hate me today. You're going to hate me because you're going to realize that all of the work that you have been doing with the difference quotient the last quarter of the school year, basically, to find the derivative of polynomials was unnecessary. But as is always the case in mathematics, we have to learn to walk before we can learn to run. We always learn the hard way before we would learn the easy way because we have to understand why things are the way they are in math and where they come from. Okay? So let's begin at the beginning. If we start with the simplest of all functions, the constant function, f of x equals c, this would be the horizontal line y equals c in the coordinate plane. Everybody can envision right now like y equals 6, horizontal line. We already know that the derivative of any function at a given point a is the slope of the line tangent to the function at a. So if you have a horizontal line, a constant function, the slope is always 0. So the derivative of any constant function must be 0. So therefore we have our first rule here. The derivative of a constant function, d dx of c, is equal to 0. Then we start thinking about polynomial functions. So linear, quadratic, cubic, quartic, so on and so forth. We have found the derivatives of many polynomials in the past, again, the long way, using the difference quotient. And I don't know if you've noticed this yet, but they always seem to follow the same pattern. The derivative of a polynomial is always 1 degree less than the function it was derived from. So if we think about derivatives of any power function or any polynomial function in general, the derivative of something that is linear, like 1x, the derivative would just be 1. Or in other words, the derivative of a linear function is just the slope of that function. The derivative of 6x plus 2 would be 6. The derivative of negative 3x minus 5 would be negative 3, so on and so forth. And in fact, every polynomial follows the following pattern, and that is that you take whatever your exponent is, you bring it down in front of your variable, and then you subtract 1 from the exponent, and that becomes your new power. Now, when you're bringing that exponent down in front, if there is already a coefficient there, you multiply the old exponent times the coefficient. That becomes the new coefficient of the first term of your derivative, and then you subtract 1 from the exponent. And you just do that to every term in the polynomial, and that gives you your derivative. I think this will make more sense if we look at a concrete example where we're actually dealing with some real polynomial terms. Example 1 says, use the derivative of a power function rule to find the derivative of f of x equals x cubed. Prove your answer is correct using the definition of a derivative. All right, so the first thing that we're going to do is we are going to do this according to the power rule, which we have just learned. So the power rule says that if we have the function f of x equals x cubed, then the derivative of this function, f prime of x, would mean we would have to take our exponent, which is 3, and bring it down in front of the term. And then we would have to subtract 3 minus 1, which would give us a new exponent of 2. So the derivative of x cubed is 3x squared. So easy, right? So now let's prove that this shortcut power rule actually works by using the definition of a derivative, or in other words, the difference quotient, which we have been doing, like I said, for about the past 8 weeks. So f prime of x is going to be equal to the limit as h approaches 0 of f of a plus h, which would be, or x plus h, which would be x plus h cubed, minus f of x, which is x cubed, all over h. And then we just have our algebra to do now. So f prime of x is equal to the limit as h approaches 0. X plus h cubed is going to be x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. And this is all over h. Now we get to cross out our terms that cancel, which in this case is just x cubed and negative x cubed. All three remaining terms contain h. So if we factor the h out, we end up with 3x squared plus 3xh plus h squared over h. And then we can cancel the h in the numerator and in the denominator. So those h's canceled, and we get f prime of x is equal to the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And now when we evaluate the limit and we plug in 0 for h, we get 3x squared plus 3x times 0 plus 0 squared. So both of those terms disappear. And what are we left with? We are left with 3x squared, which is the exact same answer we got when we did the power rule. All right? Don't hate me. You don't have to do the definition of a derivative. You don't have to do the difference quotient anymore when asked to derive a polynomial unless I ask you to compare and contrast or to prove the power rule using the definition of a derivative. From this point forward, if I ask you to find the derivative of a polynomial, you get to shortcut it and use the power rule. The problem that we just did was just a monomial. It was a single term. Well, what if we've got more things going on? What if we have coefficients in front of our terms? I already kind of addressed that. When you bring the exponent down in front, if there's a coefficient, you just have to multiply. So the constant multiple rule addresses that. It says that the derivative of some constant times a function is equal to the constant times the derivative of the function. Example, if we have f of x equals 2x to the fourth, and I asked you to find f prime of x. So f prime of x would be equal to 2 times d dx, or the derivative with respect to x, of x to the fourth, right? So you can just move that 2 in the front. Now, most of the time we do this step in our heads. So this would be 2 times. Now, if we use the power rule on x to the fourth, we would bring the 4 down, and then we would change the exponent to a 3. But again, we have to multiply that constant in front times the 4, so we would end up with 8x cubed. So that's an example of the constant multiple rule. The sum rule just says that if we're asked to find the derivative of two functions that are being added together, your result will be finding the derivative of the first function, finding the derivative of the second function, and then adding those two together. That is your answer. And the difference rule, the same thing. If we're subtracting two functions, find the derivative of the first, find the derivative of the second, and then find the difference of the derivatives. Example 2 says to prove or to differentiate f of x and then prove your answers correct using the definition of a derivative. So just like example 1, we are going to do it both ways just to show that we do get the same answer. So let's start with the power rule again, our new fabulous shortcut. But this time we have 3 terms. F of x is equal to 2x squared minus 4x plus 7. So again, I am just going to differentiate each term using the power rule. So my first term, I have that 2, but then I'm going to bring down the exponent 2, and then I'm going to subtract 1 from my exponent, so 2 minus 1 makes this a 1. The second term, you really have a 1 right there on the x. We don't think of it that way, but we do, right? And so you're going to have minus 4 times 1, and then x, 1 minus 1 gives me an exponent of 0. And then the derivative of a constant term is 0. Now, The steps that I've shown here are actually more work than you'll typically show on your paper. You're going to get so fast at this that you're just going to be doing it in your head immediately. So f prime of x is going to be equal to 4x minus 4, right? Because the derivative of negative 4x is negative 4. We talked about that earlier on in the notes. It's the slope. The derivative of a linear function is the slope. So the derivative of the term negative 4x is a linear term. The derivative would be negative 4. Any derivative of a constant term, plus 7, that's like our horizontal line, right? Derivative of a constant is 0. So f prime of x here is 4x minus 4. Now let's do this according to the definition of a derivative, which again means using our difference quotient. So f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h, so it'll be 2 times x plus h, quantity squared, minus 4 times x plus h, plus 7, minus f of x, we need a bracket, 2x squared minus 4x plus 7. And this is all divided by h. And now we do our slow, careful algebra. So this is going to be equal to the limit as h approaches 0 of x plus h quantity squared is x squared plus 2xh plus h squared, and I'm going to distribute my 2 right away. So I'm going to get 2x squared plus 4xh plus 2h squared. Then I'm going to distribute the negative 4 to the x plus h, negative 4x, negative 4h. I have my plus 7, and then I have to distribute the negative through the bracket, so negative 2x squared, positive 4x, and negative 7. And again, all divided by h. Now I get to cross out terms that cancel. Positive 7 and negative 7, negative 4x and positive 4x, positive 2x squared and negative 2x squared. My remaining 3 terms all contain h. So let's factor that h out right away. H times 4x plus 2h minus 4 divided by h. The h's cancel. So this is equal to the limit as h approaches 0 of 4x plus 2h minus 4. And when we plug in 0 for h, we get 4x plus 2 times 0 minus 4. That term disappears, and we end up with f prime of x is equal to 4x minus 4. So again, we get the same answer, but don't you prefer the power rule? I know I sure do. It's been a long time coming. I've been waiting for this day for a while. All right, so that's how we differentiate polynomial functions, but what about other functions? And the next one that we're going to talk about is exponential functions, specifically e to the x, where our base is e. Okay, so this whole next section here is a proof, all right? You do not have to memorize this. You don't even have to be able to reproduce it. But what I hope is that as you go through it slowly and carefully and you think about each step in the proof, you understand what's going on. So if we want to figure out the derivatives of exponential functions, we begin by using the definition of a derivative to differentiate the generic function f of x equals a to the x, where a could be any base, right? So then f prime of x would be equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Well, when we plug it in, we get the limit as h approaches 0 of a to the x plus h power minus a to the x over h. And then we can separate that a to the x plus h into a to the x times a to the h, and we can factor an a to the x out of those 2 terms. And then it says, no, since a to the x doesn't depend on h, we can move it to the front of the limit. So then we get to this step right here, which is our derivative is equal to a to the x. So the original function that we started with is going to be part of our derivative answer. So a to the x times the limit as h approaches 0 of a to the h minus 1 divided by h. So what remains in that box is the limit that represents the value of the derivative of f at 0, right? That is the limit as h approaches 0 of a to the h minus 1 over h, which is f prime of 0. So basically, that bit of work there just shows that any exponential function or any exponential function with a base of a, where a can be any number, if it's differentiable at 0, then it's differentiable everywhere, and that the answer to the derivative is always going to be the function itself, a to the x, times the value of the derivative at 0. This equation says that the rate of change of any exponential function is proportional to the function itself, meaning it has a to the x in it. So then the next question is, how do we figure out what that f prime of 0 part is? Because substitution won't work. We can use a table of values to evaluate this limit. So what if we let a be 2? Or what if we let a be 3? You can see that table of values there where they looked at those two different bases, a is 2 and a is 3, and they plugged in different values getting closer and closer and closer to 0 on the right-hand side of 0, and they populated their table. So in the table are examples of that exact limit that we're trying to figure out when a is 2 and when a is 3. And basically what they came up with is, for a equals 2, the closer and closer and closer they get to 0, the value of f prime of 0 is equal to about 0.69. Interesting. That happens to be the natural log of 2. Okay, FYI for future reference. When a is 3, it looks like the limit basically becomes 1.10. FYI. That value is the natural log of 3. So from the equation for the derivative of an exponential function, they have that the derivative of 2 to the x is going to be 2 to the x times this value, 0.69, which, as I said, this value is actually natural log of 2. And then when our function is 3 to the x, the value of the derivative is 3 to the x times 1.10, which happens to be the natural log of 3. So now we're trying to figure out, well, all right, this is interesting. Natural log of 2, 0.69. Natural log of 3 is 1.10. Is there some base there that would make that value times my function be 1? And of all possible choices for the base a in the above equation, the simplest differentiation formula occurs when f prime of 0 is 1. And the magic number that makes that happen is a base of e. So here we have the definition of the number e. E is the number such that the limit as h approaches 0 of e to the h minus 1 divided by h is equal to 1. Okay? And from that definition, we get the derivative of the natural exponential function. If we let our base of our exponential function be e, then f prime of 0 is 1. We get the following important formula. So here's the big takeaway of that whole last slide. The derivative of e to the x is itself, which is kind of fascinating. The derivative of e to the x is e to the x. Okay, so let's use that and try to do example number 3. Notice that I'm beginning with y equals e to the x plus 1 power plus 1. So the first thing I'm going to do is I'm going to rewrite e to the x plus 1 as e to the x times e to the 1. Okay, remember, powers with the same base, you add their exponents. So if you want to unadd their exponents, you'd be multiplying powers with the same base. And then I have plus 1. Well, e to the first power, remember, is just e. So I'm going to write this as y equals e times e to the x plus 1. So now if I want to find the derivative, then y prime is going to be equal to the derivative, so d dx of e times e to the x plus d, the derivative, d dx of that constant term 1. Well, as we talked about earlier, if you have a constant that doesn't depend on your variable, you can bring that in front of your derivative, and that just gets multiplied in your answer. So y prime is going to be equal to e times the derivative of e to the x plus the derivative of 1. We're almost there. So y prime is going to be equal to the derivative of e to the x is e to the x. So e times e to the x plus the derivative of any constant is 0. So my answer is y prime is equal to e times e to the x, or we could write that as y prime is equal to e to the x plus 1, because remember that has an exponent of 1 on it. We could combine it back. So there's the answer for number 3. And again, on this step right here, you might want to put a little note here that e to the first is just a coefficient that does not depend on x. Move it to the front. Just a little note for you later as you are looking back. Example 4 is our last example today. It says find f prime of x, so find the derivative of f of x, then graph the function and its derivative and use them to explain why your answer is reasonable. All right, so let's use our new best friend, the power rule, to find our derivative f prime of x. So again, writing this as simply as possible, I think we can skip some showing of some steps here and just do the math in our heads. If we bring the exponent down in the front, we're multiplying the exponent 2 times the coefficient 2. 2 times 2 is 4. And then our exponent, it was x squared, so now it becomes x to the first. Our next term, we have the negative in front. We bring the 4 down. There's a 1 there. You get an invisible 1. 4 times 1 is 4. And then we have to subtract 4 minus 1, which gives us a new exponent of 3. So the derivative of f of x is 4x to the first minus 4x cubed. Okay, so thinking about what we have here, let's just kind of jot some information down. F of x is a quartic polynomial. F prime of x is a cubic polynomial, as it should be, because we should always be 1 degree less if we are differentiating a polynomial. All right, let's take a look at the graphs here. So I'm going to sketch a coordinate plane, and then we'll use our graphing calculator to graph these for us. So grab your graphing calculators, everybody, and let's go to y equals. If you've got anything in there, clear it out. And we are going to put in f of x first, which is 2x squared minus x to the fourth. Okay, and then our second function is our derivative, which is going to be 4x minus 4x cubed. All right, and then let's just do a zoom 6. And as you can see, the blue function is our quartic polynomial, our f of x, and the red function is our cubic polynomial, which is our derivative of the quartic. So if we were to just kind of sketch a graph of the two functions, let's go back to our paper here. Our quartic polynomial had some x-intercepts at -2, 0, and 2. And it had points at -1, 1 and +1, 1. So our quartic polynomial is pretty easy to graph. looks kind of like a curvy capital M. And this was our f of x. And then our f prime of x, our cubic polynomial, passed through 0, 0. And it had a point at x-intercept at -1 and +1. And it looked something like that. All right, so let's talk a little bit about what we know. If we think about where our zero slopes are on our f of x, on our blue graph, those should line up with our x-intercepts on our red graph, and they certainly do, right? Zero slope, x-intercept, zero slope, x-intercept, zero slope, x-intercept, okay? So let's add that to our list. Zero slopes on f of x align with x-intercepts on f prime of x, okay? The next thing we should think about is our increasing and decreasing. So f of x appears to be increasing to begin with up to about -1, and that's where f prime is above the x-axis. Then f of x decreases from -1 to 0, and our f prime is below. Then it increases from 0 to 1, our f of x is above, and then it decreases from 1 on, and our f prime of x is below. So increasing, decreasing on f of x matches positive, negative values on f prime of x, okay? And then finally, let's talk about inflection points. Remember, inflection points are where our concavity changes. So if we look at our f of x graph, we are concave down until about right here. And then we switch to being concave up right here. And then we switch again to being concave down for the remainder of the graph. And what do we notice about these inflection points right here? Well, those inflection points line up with turning points on f prime of x. So that's the last thing that I want to note, is that inflection points, IPs, on f of x align with turning points on f